This is GM Word of the Week, and I'm Fiddleback. Story. As fantasy gamers and as podcasters, obviously we at the Word of the Week love a good story. Or any story, really. But then, that actually has nothing to do with being gamers and podcasters. Really, those are just some of the ways we express our love of stories. Because all human beings love stories. In fact, there's good evidence to suggest we don't just love stories, we need stories. Take the study done in 1944 at Smith College, for example. There, psychological researchers were curious just how strongly the concept of story was wired into the human brain. So they did this experiment. They showed a short film to a bunch of participants, probably hapless social science students, whose participation in a certain number of department studies was required to get a good grade. That's how it usually happens. Anyway, the film showed a couple of triangles and circles moving around a blank field, and there was a rectangle too, just sitting there. And they asked the participants to explain what had happened in the film they just saw. One participant wrote down that the film had depicted some polygons moving around. He was probably an engineer or physics student trying to make a quick buck by participating, is our guess, given that pedantic answer. What's interesting, though, is how every other participant responded. The other participants described a scene that depicted a pair of triangles fighting, while a worried circle paced around. Some just described the fight, others ascribed motivations and personalities. Some even blamed one of the triangles specifically, stating that it was obviously blinded by rage and frustration, while the other triangle was just an innocent young victim of the rage. We have to stress, again, that the film literally depicted a bunch of moving shapes, exactly as the one boring student described. That's all. Everything else was invented by the participants independently of each other. People are so hardwired to see stories that they can imagine an entire dramatic prequel to Flatland in a bunch of moving shapes. Flatland, you know, the famous satirical critique of Victorian social structure presented allegorically as the story of a bunch of two-dimensional shapes discovering the third dimension that was barely noticed when it was published in 1884, but without which a lot of people wouldn't have had any idea why Einstein was so great in the 1920s. Alright, let us explain. The story starts with a British schoolmaster, philosopher, theologian, and mathematician named Edwin Abbott Abbott. No, we did not stutter. See, he was the son of Edwin Abbott and Jane Abbott. And when we say Jane Abbott, we don't mean she was Jane something or other and changed her name when she got married. She was Jane Abbott, née Abbott. Because Jane and Edwin Sr. were first cousins, you see. So Edwin Abbott married Jane Abbott, and they named their son as uncreatively as possible after both of themselves, Edwin Abbott Abbott. All of that aside, Abbott was well educated in the City of London School and St. John's College in Cambridge, and he was a model student and was awarded a fellowship. He did advanced coursework there in literature, theology, mathematics, science, and philosophy, a bit of everything basically, but then he met a very nice lady named Mary Elizabeth Rangeley. And he wanted to marry her, but he couldn't, because at the time, college fellows were not allowed to marry. They were basically an academic sort of priestly caste, and this was the Victorian era where there were a lot of social and cultural rules. And if you're keeping a score of Victorian ethics at home, that's college professors can't marry, first cousins can. So Abbott resigned his fellowship to marry his sweetheart, and they had a nice marriage and raised a pair of kids and lived happily ever after. Abbott went on to teach at King Edward's School and Clifton College, and then returned to his alma mater at the City of London School to take the post of headmaster. And he was widely recognized as a very talented educator. He developed new methods of instruction, an innovative new curriculum, and had a natural talent for teaching. He made certain things like science education compulsory through high school. Well, the equivalent then of high school. And he also wrote a lot of books about grammar, literature, philosophy, and religion. And he loved writing so much that he retired at the young age of 50 so he could have more time to write. And in 1884, he wrote a weird little novella called Flatland, a romance of many dimensions, under the pseudonym A. Square. Now, Flatland was an interesting little melding of social critique and geometry. It told the story of a two-dimensional world filled with living polygons, squares and circles and triangles and lines and stuff. Males were polygons, and their status was determined by the number of sides they had and how regular those sides were. They had a complicated caste structure. Females were lines. And all of this led to some odd features in Flatland. First, what you have to understand, and Abbott goes into great detail about this in the book, what you have to understand is that if you are a two-dimensional shape in a two-dimensional world, everything looks like a line to you, because you're looking at totally flat shapes edge on. Now, there was a sort of fog in Flatland and some luminance, so you could tell how far away an edge was from you and whether it was receding into the distance. So you could tell when you were looking at corners and seeing different edges of a thing. There's even some diagrams in the book to help the reader out, because it's hard to imagine, but not impossible. The second issue is that the women were lines. And if there was a woman coming straight towards you, she was an infinitely tiny point you could barely see. And if she walked into you, she'd stab you dead. Yeah, we kid you not, that was part of the book. So society had enacted all of these laws about how women had to use different doors than men and approach from certain directions and constantly hum so that men would know where they were because, well, they could turn into invisible stabbing blades just by walking in the wrong direction relative to you. And these rules actually created a lot of discussion about things like class structure and gender roles. Flatland was a very Victorian classist and sexist place, see, and it is thrown into further chaos when a three-dimensional sphere shows up. Anyway, it's a neat little book and fun, if a little weird. But in 1884, it just didn't really catch on. It sold okay, but it would have been completely forgotten. But then, along came this crazy-haired German dude named Albert Einstein. In 1905, Albert Einstein found himself thinking about a weird problem in physics, the problem of relativity. See, for physics to work, the laws of physics have to work the same for absolutely everyone everywhere. So, if you're throwing a ball around, that ball has to follow all the laws of motion, even if you're throwing the ball while you're on a moving train, or on a planet that is spinning at 1,000 miles per hour and hurtling through space at upwards of 450,000 miles per hour. If it didn't work the same way, it wouldn't have taken us so long to decide whether the Earth was moving, or the Sun was moving, or both were moving, or whatever. Without that consistency, you'd never get confused when you sit in a car and the car next to you starts moving about whether that car is moving or you've accidentally taken your foot off the brake pedal and started rolling into traffic. Now, we've known about that relativity thing forever. Well, at least since Galileo imagined a dripping candle on a steadily sailing ship. Two people playing ball on a moving train play ball exactly the same way as if they were on the ground and can ignore the train's movement completely, unless it goes around a curve or breaks suddenly. But Einstein was doing some work with electricity and magnetism, and he discovered a problem. At its simplest, magnetism is a force that is created whenever something with an electrical charge moves. So if you put an electrically charged ball on a train, say it's statically charged, even if it is stationary relative to the train, magnetism will still happen as the train moves. And so you can't discount the movement of the train. And suddenly, hundreds of years of Galilean relativity was broken by one careless guy who decides to rub a balloon on his head while on board a train. And that was a problem because not only are grown men sticking balloons to train ceilings annoying, Galilean relativity was the rule that assured us that physics wouldn't stop working if we moved the wrong way. Eventually, Einstein figured out how to solve the problem. Everything would be okay as long as light always moved at the speed of light. Now, you may think that's a pretty obvious thing to say, but it wasn't. Not the way Einstein said it. Think of light as a moving thing, like a stream of little pellets of light called photons, and imagine them being fired at the front of a flashlight. A flashlight is basically just a photon machine gun, and each light bullet shoots off at 186,000 miles a second. Fine. Now, imagine you're riding on a train that is going at a ridiculously high speed, like 100,000 miles a second. Some sort of Galaxy Express, maybe. Now imagine turning on a flashlight. Well, you'll see the little bullets of light shooting out of the flashlight at 186,000 miles a second. But a person standing on the platform as the train speeds by? Well, he would see the photons traveling at a different speed. They should pick up the speed of the train just like a thrown ball picks up the speed of the train when you play ball on a train. Well, Einstein said everything would be fine and physics wouldn't get broken as long as light never did that. As long as light always traveled at 186,000 miles per second wherever you were standing and however the flashlight was moving. The guy on the platform would also see the light traveling at 186,000 miles per second out of the flashlight, and consequently, the train would be keeping pace with it, and therefore the light would take a long time to get to the front of the train. Crazy? Absolutely. It took Einstein another 10 years or so to figure out how the heck that could possibly work. That's why his first theory was called special relativity, and the second theory was called general relativity. The first one was missing some pieces. The second one worked for everyone, everywhere. And it was based on the idea that time was a part of space, a fourth dimension. And time and space could be bent. Like the universe is a rubber sheet made of space-time, and time is just movement at a right angle to reality. Seriously. Now, if you weren't already a physicist, this was bonkers. But at the same time, you were hearing how this German wunderkind had broken physics and then saved it again because time was just the fourth dimension. You had length, width, height, and time. And all at right angles to reality. And suddenly, there was a lot of money to be made in selling books that explained how the heck time could be a fourth dimension and exist at right angles to space. Except there already was a book that explained that. Edwin Abbott had included a preface to Flatland that basically said, look, I know the idea of a sphere visiting a flat two-dimensional space is crazy. It'd be just as crazy as if someone came along and tried to convince you that there was some fourth dimension to your universe that they could perceive and exist in, but you couldn't. You'd only be able to see a little partial projection of that fourth dimensional person that exists in your three-dimensional frame of reference. But that'd be bonkers, so let's hope a crazy German scientist doesn't appear in 30 years and try to tell us that stuff is real. And suddenly, Flatland became popular reading. No, really. The only reason anyone is still talking about Flatland today, and the only reason it was reprinted instead of being forgotten in 1884 is because someone saw the preface and said, wait, this is that relativity stuff that Einstein is saying, and then convinced people to read it. What does that story have to do with anything, with our love of stories, and with psychologists and anthropologists experimenting with why stories are so hardwired into our brains? Well, we'll tell you. See, we humans have been passing down stories for pretty much our entire human history. The story of stories starts 30,000 years ago. That's the age of the oldest cave paintings we've found. They were discovered in 1994 by Jean-Marie Chauvet, Eliette Brunel, and Christian Hilaire. The three spelunkers were exploring the banks of the river Ardèche in south-central France. It's an offshoot of the Rhone River, and they were near a really spectacular natural rock bridge known as the Pont d'Arc. As they explored a natural cave, One of them noticed some red smudges on the ground and said, "Hey, is this paint?" And the other two said, "Yeah, duh, look." And they pointed at the hundreds of paintings and engravings adorning every wall of the cave. By the way, we're only slightly embellishing that story. That's kind of how it actually happened. "Hey, this looks like a smear of paint. Weird. Oh, holy cow!" They reported their findings, and archaeologists were on it like social science students on a thesis project that involves just filling out one 5-minute questionnaire. Archaeologists determined that the cave had been inhabited during 2 different periods. The first about 35,000 years ago and the second about 28,000 years ago. And then the cave had been sealed by a cave-in until the amateur spelunkers found a way in. So it was an archaeological jackpot. Now what does this have to do with stories? Well, among the hundreds of paintings, there were just images like handprints and shapes and stuff. But there were also elaborate scenes depicting animals and people hunting animals and gathering plants and berries and nuts and things. And those paintings told us a lot. They told us what the Paleolithic people of the region gathered and ate, what they hunted, primarily reindeer, bisons, and aurochs, what they competed with, cave bears and cave lions, and how they hunted, what weapons and tools and tactics they used. Fast forward thousands of years, and you can see similar art in the hieroglyphs and pictographs of the Egyptians. Those hieroglyphs, whose name comes from the Greek word hieros, or sacred, and the Greek word glyph, or carving, hieroglyphs are recognized as one of the oldest forms of written communication on Earth, being more than 5,000 years old. And they are a sort of halfway form between written language and picture. The earliest documents using hieroglyphs were actually more like diagrams and illustrations than anything else. Now gradually, in Egypt and Phoenicia, pictographs and diagrammatic glyphs changed into what we recognize as symbolic language, written language, letters and alphabets and stuff. But what didn't change is what people were recording. They were recording stories. This hit a high point in ancient Greece around 750 BCE, when the Iliad got recorded by Homer. Because what we saw there was the transition from oral story traditions to written stories. And the Iliad is believed to be the first oral story transcribed and preserved in written language that still exists today. Cave painting, pictographs, and written language all evolved to pass stories from one generation to the next, and in fact, verbal language did the same thing. Humans have been telling stories any way they can for at least 35,000 years, and they have been looking for ways to record those stories. And that is what is hardwired into our brain, very, very strongly. And every culture on Earth has had in the past an oral storytelling tradition. Stories passed on from one generation to the next, remembered and retold time and again. Some cultures, like the Greeks and the Egyptians, eventually figured out the written language thing to record their stories. Others just kept doing the oral thing, like many pre-Columbian native North American tribespeople. But why stories? Because they are a very effective means of passing on information and getting it to stick in your brain. This is how you hunt reindeer. Watch out for this cave bear. Don't eat this berry, it'll kill you. How would our caste-based society look to an outside objective observer, and should we think about that? This is how to imagine a universe that is way more complicated than what you can see. One study at Stanford University demonstrated that most people are 22 times more likely to remember details from a story than to remember raw facts shared alone. And that is because of a few key factors of neuroscience. One of the most prominent is that your brain actually can't tell the difference between imagined experiences and real experiences. It responds to both the same way. So if someone tells you a story of escaping from a cave bear, and you really, fully imagine that story and get really engaged, your brain responds to that the same way as if you were actually remembering your own escape from a cave bear. About 6 years ago, neuroscientist Gregory Burns at Emory University conducted and published an interesting experiment regarding precisely this. participants in the study were given a novel to read, Pompeii by Robert Harris. It's an exciting novel about a guy outside the ancient city of Pompeii as the volcanic Mount Vesuvius starts to erupt. This is based on the real historical event, by the way. Spoiler alert, Pompeii loses to the volcano. Big time. The hero of the novel notices the volcano is acting strange and tries to convince people it's going to explode, as he also tries to get back to the city in time to save his girlfriend. The reason the researchers chose the book is because it is a dramatization of historical events, but it has a very strong and exciting narrative that connects the story together through the eyes of an emotionally sympathetic protagonist. In short, they chose it because they thought it was a good novel. The participants read the novel in chunks, and after they read each chunk, Burns and his team stuck them in a functional MRI machine to check out their brains. An fMRI is a device that uses magnets to vibrate hydrogen atoms in water and fat molecules and thus generate a picture of the inside of the human body. Well, that's an MRI. An fMRI can actually detect minute changes in blood flow, and so you can actually watch the organs, like, say, the brain, work by seeing which parts are using how much blood. Long story short, the fMRI scans showed a great deal of interconnectivity in the brain. The language interpreting parts of the brain lit up, sure, but so did the parts of the brain associated with movement and sensation. This is called grounded cognition, by the way. It's a neural phenomenon in which thinking about or remembering an activity or experience like running makes your brain light up as if it's doing that thing. And apparently, it also happens if you read a story about doing those things. As Burns himself said, his study showed that a good story doesn't just put you in someone else's shoes figuratively, it also does it biologically and neurologically. And that is why stories are such an effective means of passing on information. Because they engage your whole brains, all of the parts, and make facts and information memorable. They generate connections between facts, emotions, motor skills, and sensory impressions, all through the power of human imagination. And that is why we here at the Word of the Week consume stories as if our lives depended on it. Because for 30,000 years, our lives have depended on it. This has been GM Word of the Week. It's written and researched by The Angry GM and produced by me, Fiddleback. You can support us on Patreon at patreon.com/GMWordOfTheWeek. You can find more at gmwordoftheweek.com and theangrygm.com.